Happy learning! Today we're going to be talking about relative maxima and minima and curve sketching. So we're going to start today by stating a theorem. The theorem says if f prime of x, so if our derivative is positive for all x in some interval, so this is saying if our derivative is positive when x is between a and b, okay, that means the slope of the tangent line is pointing in this direction, right? It has a positive slope, which means our function is going to be increasing. All right, so the derivative, if our derivative is positive, we know that our function, so like the graph of our function is increasing. Similarly, if f prime of x is negative for all x, on the interval ab, then f is decreasing on that interval. All right, so the derivative, whether it's positive or negative, tells us if our function is increasing or if our function is decreasing. All right, so let's take a look at an example. So suppose I have a graph like this. Let's say this is at -1. This is at 2. So our function is increasing from -infinity to -1. So f prime of x is positive on the interval -infinity to -1. F prime of x is negative between -1 and 2. And then we increase again. So f prime of x is positive from 2 to infinity. This point here that's taller than all of its neighbors, this is called a relative maximum. So this point is the relative maximum. Right? It's not the highest point on the graph necessarily, but it's bigger than all of its neighbors. Right? So whatever mountain nearby for you is the tallest, that's a relative maximum. Mount Everest, the peak of Mount Everest, would be the global maximum. Okay, this point down here, this low point, this is a relative minimum. All right, and we're going to be interested in finding the locations of the relative maximums and the relative minimums, right? These are going to be 2 bits of information that will be useful when we go to curve sketching. Also, if this is like a profit function and we want to maximize our profit, knowing where the relative maximum is would help us maximize our profit. Okay, so the theorem, this theorem tells us how to find candidates for relative max or relative min. It says if f has a relative max or relative min at x equals a, then one of two conditions holds. It is either the case equals 0, or f prime of a does not exist. Okay, so remember, what does it mean for the derivative to be 0? It means the tangent line is horizontal, right? And you can see when we get to this peak, the tangent line is horizontal. And for does not exist, maybe there's a sharp corner in our graph. And so there the derivative wouldn't exist, but you could imagine a sharp corner could be like a low point of a graph like this. Right? That's a low point of the graph, and the derivative doesn't exist there. So this is where the two candidates for where relative max and relative mids are. Okay, we call these x values, right? So this number here, a, we call these values the critical values. All right, so if you're ever asked to find the critical values, it's just when is the derivative 0 and when is the derivative undefined. So find the values when our derivative is 0, find the values when our derivative is undefined. Okay, so what I want to talk about now is called the first derivative test. Okay, what does the first derivative test do? We use it to find the relative max or relative min values of a function. All right, so if we want to find the relative max and the relative mins, there could be multiple, right? You could imagine a graph that bounces up and down a lot, would have many relative maxes and many relative mins. We're going to use the first derivative test. Okay, so the first step in the first derivative test is to find the first derivative. Okay, step 1, find the first derivative. Step 2, we want to find the critical values. So find when f prime of x equals 0 or f prime of x does not exist. All right, so this is finding the critical values, step 2. This is going to be some x values. Right, maybe we'll get like x equals 1, x equals 3, x equals 7, and so forth. Okay, so we have a few x values. We need the y values. So substitute these values into f of x. This gives the critical points. Right, so when we sub it into our original function, we get the y value as well. So now we'll have an x and a y. That means we have a point. Okay, and then the next step is going to be how we determine whether we have a relative max, a relative min, or potentially these critical values are neither. Okay, so step 4 is evaluate the derivative at a value of x to the left and to the right of each critical point. And we're going to make a sign diagram. We're basically going to check, is the derivative positive or is the derivative negative? Okay, and so we're going to see, okay, on this interval our derivative is positive. On this interval our derivative is negative. Okay, and so there's going to be times where we go from positive to negative. If f prime goes from positive to negative, so our function goes from increasing to decreasing. Increasing to decreasing. At this point, that's a relative max. If f prime of x goes from negative to positive, we go decreasing to increasing. We have a relative min. Okay, and then using all of this information, we'll have a general sense of what our function looks like, the graph of our function looks like. So step 5 is let's sketch the graph. Okay, so let's do an example. Right, just to recap, we're going to find the derivative, find when it's 0 or undefined, or undefined. Substitute these values into our original function to get at its critical points, and then we're going to check with the first derivative whether our function is increasing or decreasing between these critical points. All right, so sketch the graph. Of the function f of x equals 1/3 x to the third minus x squared minus 3x plus 2. All right, so what we want to do is we want to locate the relative maxes and relative mins, and then check if our function is increasing or decreasing on each of these intervals, and then we'll connect the dots, and that will be what our curve looks like. All right, so first step is we want to find the derivative. This function here is just a polynomial, right? There's no products, there's no quotients, no chain rule. We just use the power rule here. Bring the power in front, subtract 1. So bringing the 3 in front, 3 times the third is 1. This is just x squared minus 2x minus 3. We want to find when the derivative is 0 or undefined. This is a polynomial. It's never undefined. So when could something be undefined? Well, if there was division by 0 or the square root of a negative. All right, there's no division by 0. There's no square root of a negative here. So we just have to find when this thing is 0. So we're going to take this, and we're going to set it equal to 0. This is just a quadratic. So we could use the quadratic formula, or we could just factor. All right, so we have two critical values. Our critical values are -1 and 3. All right, so this is where if there was a local max, it occurs at one of these values. If there was a local min, it occurs at one of these values. There's no other place where a local max or a local min can occur. All right, so what do we need now? We need our function evaluated at these points. And we need that for when we actually go and graph our function. So let's evaluate f of -1. So it's not the derivative. We're evaluating the actual function at this point to get the y value. If we sub in -1 into for x, we get the value of 11/3. And we also have to evaluate f of 3. So if we sub 3 in for x, we get the value of -7. Okay, and so now what we're going to do, so these are 2 points on our graph, right? We have the point -1, 11/3, and the point 3, -7. When we go and sketch our graph, those are going to be 2 of the points we include. Now we need to determine where is our function increasing and where is our function decreasing. All right, so the way we do this is we take the number line and we're going to break it up at each of our critical values. So break it up at -1 and we're going to break it up at 3. Okay, and then we're going to pick a value on each of these intervals. I like to call these test values. So a test value is just any number that's less than -1. So -2 could be our first test value. Then we need a test value that's between -1 and 3, so 0 is a good option. And then we need a test value that's bigger than 3, which is maybe 4. I mean, you could pick any number that's bigger than 3, but 4 is a good one. And what are we testing? We're testing whether the derivative is positive or negative at this value. All right, so we need f prime of -2. And so we could just sub it into our derivative function. We could also sub it into the factored version of our derivative function. If we sub it into the factored version of our derivative function, we could easily check if it's positive or negative. Right? If we sub in -2, -2 minus 3 is negative. -2 plus 1 is also negative. A negative times a negative is positive. All right, we don't care what the value is. We just care if it's positive or negative. And so what this is saying that on our first interval here, our function is increasing. Right? Our derivative is positive on this interval, so our function is increasing. Now let's find the derivative at 0. A negative times a positive is a negative. So our function is decreasing. And then finally, with 4, we have a positive times a positive. We get a positive. Okay, you might be wondering, Dr. Wesselcouch, does it always alternate? No, it does not always alternate. So you do have to check each of the intervals. Okay, so it does not always alternate. It just happened to alternate in this case. So you do have to check each interval. Okay, and so just by looking at our little sketch here, we know there is a relative maximum at -1, and we know we have a relative minimum at 3 because our curve goes from decreasing to increasing. So now we could sketch this curve. Let's include our critical points. So -1, 11/3. 11/3 is just under 4. And we also have the point 3, -7. All right, so to the left of -1, we're increasing. And then we're decreasing. And then we're increasing again. All right, and let's just label our critical points. So this is the point -1 11/3, and this is the point 3 -7. And you could check with Desmos that this does a pretty good job showing what our function looks like. So, like I said earlier, it's possible that some of our critical values don't correspond to relative max and relative mins. And so if that's the case, we call the critical value a point of inflection. So let's define that. So if f prime of a equals 0, but f prime of x does not change signs at x equals a. So maybe we go from positive to positive or negative to negative. Then f has a horizontal point of inflection at x equals a. All right, let me give you an example. If we have the function f of x equals x to the third, let's find its critical point, and then we could show that it's actually a horizontal point of inflection. So f prime of x is 3x squared. We're going to set that equal to 0. That gives us x equals 0. Our only critical value is x equals 0, and that's when we sub that into our original function, that's the point 0, 0. We could use -1 and 1 as our test values. F prime of -1 is 3 times -1 squared, positive. F prime of 1, also positive. Okay, so our curve goes from increasing to increasing, but it levels out momentarily at x equals 0. So what would it look like? At the point 0, 0, there is a horizontal tangent. So the graph will look something like this. So if you've ever seen the function y equals x to the third, it should look something like this. Okay. Let's do an application. The weekly sales y of a product are given by y equals 100x over x squared plus 100. On the interval 0 is less than or equal to x, less than or equal to 20. What is x? X is the number of weeks since the start of some campaign. And y is in thousands. Okay, so what I want us to do is find the maximum weekly sales. Okay, and so the way we're going to do this is we're going to sketch the curve, and then we're going to see what is our largest value. All right, so this function is a quotient. So we're going to need the quotient rule to take the derivative of it. All right, so we need the derivative. So how do we take the derivative of a quotient? It's bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. This is the derivative of our function. We want to find when this is 0, so it's in our best interest to clean this up first. Okay, so 100 times x squared is 100x squared minus 200x squared. That's negative 100x squared, and then plus 10,000x. That's our numerator, and our denominator is x squared plus 100 squared. We want to find when this fraction is equal to 0. A fraction is equal to 0 when the numerator is 0. So if y prime equals 0, that implies that our numerator equals 0. Okay, and we could factor this, right? Factor out a negative 100x. Okay, I made a mistake. The bottom. So you maybe have noticed this. Okay, the bottom, x squared plus 100. I wrote x squared plus 100x. So let's fix that. And there's no x here. It happens. Made a mistake. Okay, so sorry about that. If you're confused, hopefully I helped with your confusion. But okay, so we want to solve this. Let's factor out a negative 100. And we're left with x squared minus 100 equals 0. And so this gives us x equals plus or minus 10. But our interval is from 0 to 20. So positive 10 is the only solution we care about. All right, so that's a critical number. That could be a relative max. It could be a relative min. It could also be neither. All right, and so what I want us to do now is we're going to take the number line. We're not going to go from infinity, negative infinity to infinity. We're going to go from 0 to 20. And we're going to break it up at 10. All right, so test points. We could do 9 and 11. All right, so when we sub 9 into our derivative, you could check that we have a positive over a positive. That's a positive number. So just subbing 9 into our derivative gives us a positive. And subbing 11 into our derivative gives a negative. Okay, so our graph goes from increasing to decreasing. That means that at x equals 10, that is going to be where we maximize our profit. All right, so let's figure out what the maximum profit is. And the way we do that, we evaluate our function at 10. All right, so it's 100 times 10 over 10 squared plus 100. This is 1,000 divided by 200, which is 5. Okay, and so the maximum weekly sales is $5,000, and it occurred at week 10. So sorry about the mistake. Hopefully that convinces you that we all make mistakes. It's nothing to be embarrassed about. But yeah, so to recap, to find our maxes and mins, find the derivative, find when it's 0, find when it's undefined. I guess we technically should have been careful about being undefined here. X squared plus 100, that's never going to be 0, right? X squared is, it can't be negative, so x squared plus 100 cannot be 0. So we didn't actually have to worry about when it was undefined in this example, but that should be something you keep in mind. Okay, well, thanks for sticking with me, and I will see you next time. Bye-bye.